So how's everybody doing? Anybody experiencing information overload yet? Or are you ready for one more talk with cool results and cool graphs and everything? All right. So after Patrick has told you about characterization and Peter has talked to you about patient level prediction, it's now my privilege and my pleasure to talk to you about population level effect estimation. And so what I mean by population effect estimation is usually it's phrased as questions like these. What is the effect of treatment A on outcome X? Or what is the effect of treatment A on outcome X compared to exposure B, which we would often refer to as a comparative effectiveness question. And so I will go through population level effect estimation considering the three aspects that I already mentioned earlier. Evidence generation, so how to produce evidence from the data. Evidence evaluation, how do we know the evidence is reliable. And evidence dissemination, so how do we share evidence to inform decision making. And what I will do is I will go through these steps and for each of them make some recommendations on how we think in OHDSI we can improve on these aspects for population level effect estimation. But not only that, I will show you some results of work that we've done where we applied these recommendations. But let's get back to what are we really trying to do. We're trying to answer questions by patients and their doctors. So for example, a patient might walk into a doctor's office and says, "Doctor, I'm starting on Duloxetine, should I be worried about stroke?" And the doctor might not immediately know the answer and might say, "Well, let me see what I can find in literature." And the doctor might stumble on this recent paper by Lee, published this year, where they're comparing new users of SNRIs, which is a class of drug that includes Duloxetine, to the class of SSRIs. In their study, they used the Taiwanese insurance claims data. They used what we call a washout period of 12 months, meaning that they require 12 months of continuous observation prior to initiation of the treatment. They removed people using both drugs. They removed people with a prior history of head injury, with a prior history of stroke or intracranial hemorrhage. Those were the outcomes that they were investigating. They used a propensity score to account for any differences between the two groups of people, so between the users of SNRIs and the users of SSRIs. And the way that they created this propensity score is by using a logistic regression where the treatment assignment was the dependent variable. Their health outcome of interest is stroke, which they defined as first hospitalization with one of these three ICD-9 codes, so 433, 434, 436. They used a time-varying Cox regression, which they conditioned on 5 propensity score strata. So that's actually how they incorporated the propensity score in their analysis to adjust for confounding. At the end of their work, they produced this particular table, telling us the crude and adjusted hazard ratio, and showing that for ischemic stroke, they found a adjusted hazard ratio of 1.01 with a confidence interval ranging from 0.90 to 1.12 and a p-value of 0.91. So basically showing no effect. So of course this is, you would say, is a very good paper. This should really inform the patient. But I do have some questions. Specifically, I want to know how reliable is this evidence? Can the result be reproduced? And already George and Patrick mentioned that quite often we find that observational studies like these actually are very hard to reproduce. So should I be worried that this paper by Lee has the same problem that it can be reproduced somewhere else? I also would like to know, did the analysis program that they used do what it was supposed to do? Or maybe there were some coding errors or something that made it do something different. And most importantly, I guess, is I want to know, is the estimate unbiased? Specifically, I would like to know things like, does the p-value have nominal characteristics? So this p-value of 0.91, is that really a probability of 91%? And does the confidence interval really represent the uncertainty about the effect size? So are we really 95% certain that the true effect size is between 0.9 and 1.12? And the truth is that we don't really know. So how can we we maybe improve on this study. So going to our three components, and the first one, evidence generation, what are some recommendations that we can make for improving evidence generation? And in order to answer this question, we tried to replicate the Lee study. We didn't stick entirely to what they did. I don't think that's very important. What I'm showing here is just all the details of our analysis, and I underscored the things that we did different from Lee. So for example, instead of looking at drug classes, we looked at specific drugs. So we compared Duloxetine to Sertraline, which is simply the most prevalent SSRI that we can find. Instead of using a Taiwanese insurance claims database, we used the US insurance claims database, the Truven CCAE database. We restricted our analysis to people that had the indication, in this case a major depressive disorder and not bipolar disorder or schizophrenia. And we also used a propensity score, but a slightly different one, where instead of using an ordinary logistic regression, we used a regularized logistic regression. And instead of using a handful of manually picked covariates, we included all the covariates that we could construct out of the data, in this case 58,000 covariates. I could give an hour-long talk just on how we did that propensity score, but I'm not going to, because unfortunately I don't have the time. If you're interested, please come and see us at the demo for the OHDSI methods library, where we have implemented this in one of our packages. I can tell you all about it there. For now, suffice to say that we used a propensity score as well in our analysis. We defined stroke the same way, and instead of using a time-varying Cox model, we just used a fixed time Cox model, and instead of 5 strata, we used 10, which I figured might be a little bit better, but I don't have any evidence to back that up. But in all, I think it's a comparable study, maybe not completely equal, but that was not the point. The idea is that we have a starting point from which we can now maybe start to build. So what are the things that we recommend that you might do better than the Lee paper, or do differently? Well, I think we can all agree it's probably a good idea to start with a protocol where we specify our research objectives and our design decisions. And I'm not saying that Lee and colleagues didn't have a protocol, they probably did, but they certainly didn't share it with everybody. And so one thing that we in OHDSI always do is we post our protocols online. And if you want to find it, you can go to our GitHub repository where all of this information is stored. Another recommendation that we strongly believe in is that you should always make your study code open source. And that's something we did. So in this case, you can go to this GitHub repository, you will find the R code that takes you all the way from the data in the common data model, performs all the necessary data manipulations and analysis steps to get you to the hazard ratios, all the tables and all the figures that you need to basically write the paper that you might want to write. And the reason why we think that this is very important is twofold. The first reason is transparency. So anybody can now go to this open source repository and see exactly what steps we did. There is no more ambiguity about the steps that we took because they're all coded in a way that even a computer can understand it. And you can check whether or not we did actually do what we said we did. And the second reason is reproducibility. So now anybody that has data in the common data model, and we're getting more and more people like that everywhere, they can now just download this code and with a single push of the button, run this code on their database and fully reproduce the study that we did. We also advocate using validated software, meaning that in some way or another we made sure that the code actually does what it's supposed to do. And in OHDSI we rely heavily on so-called unit tests, but also simulation to verify that the software does what it does. And I'll be the first to admit that we don't yet have 100% coverage, but I think for now we at least have the most important bits of code covered with either unit tests or simulations. Lastly, you should never just run an analysis on one database. You should always replicate it on several databases. And so in this situation, we replicated this particular study on 4 databases, and more will follow. So far our recommendations for evidence generation. let's think about evidence evaluation. So how do we know that the evidence that we're generating is really reliable? Well, most study designs that people use actually have diagnostics out there that you could use. So for example, if you're doing a cohort study like they're doing here, we could investigate propensity score distribution overlap or the covariate balance. And both of these things we probably all agree are good things to do, but for example, that lead paper, which I think is actually a good paper, already didn't do these diagnostics, or if they did, they didn't share it with us. So I'm here showing you the propensity score distribution plot for Duloxetine versus Sertraline, as we computed it on the CCAE database, where the Duloxetine group had 90,000 people in it, and the Sertraline group had 175,000 people. Almost 176,000 people in it. And just to orient you to this graph, what I'm showing here on the x-axis is the propensity score, or actually I'm showing the preference score, which is a transformation of the propensity score, but that's not that important. And the blue and the red areas show you the probability distribution, or the actual distribution of this propensity score for the two groups. What this plot is telling you is that there are many people in the red group that are all the way to the right, meaning those are Duloxetine users, that based on their baseline characteristics, we could have already told you, we could have predicted that they were going to get that treatment. So there's something very fundamentally characteristic about these people that lead them to get Duloxetine. And the same is true for the blue group, the Sertraline group. Most of the people in that group, already beforehand, just based on their baseline characteristics, we were able to predict that they were going to get Sertraline and not Duloxetine. To be more formal, we could say that only 45% of patients are near clinical equipoise, so basically in the middle of the graph, where they were equally likely to get one of these treatments. Most of the patients in this analysis are systematically different from the comparator group. And therefore we know that if we're going to just compare these two groups without any adjustment, we know that the crude analysis will likely be biased because we're really comparing apples and oranges. One thing that is good to mention, but is often not something people think about, any covariate adjustment strategy that would correct for this bias will result in an impact in the generalizability of the findings of our study. Meaning that we started answering, we wanted to answer the question for one particular population, but the only way by really getting an unbiased answer is by somehow modifying the population to make them more comparable. But in doing so, we're actually starting to answer a slightly different question because it's a different group that we're really including in our analysis. So all of this we learned just by looking at the propensity score distribution plot. So here's another plot that I think is a very important one. So this plot is showing you the standardized difference of mean. So every dot in this plot is one of the 58,000 covariates that we constructed out of the data. So one of the baseline characteristics of the people in the data. And both on the x-axis and the y-axis we're showing the standardized difference of the mean. So how different is this covariate between the two populations, between Sertraline users and Duloxetine users. On the x-axis we're showing the difference before we do the stratification on the propensity score, and on the y-axis we see the stratification after. We see the difference after we do the stratification. Just to give you an example, this blue dot, which is the one that has the highest difference after stratification, is the covariate age group 10 to 14. And so we see that before stratification, the mean of that variable was 0.2, meaning that 0.2% of the Duloxetine users were in this particular age group, and 3.8% of the Sertraline users were in this age group. So that's quite a large difference for this particular covariate. We see that after we do the stratification, that difference is much smaller, so 0.3 versus 0.8. It's not completely gone, but it's, I've happened to pick the covariate that has the biggest difference after stratification. All in all, I hope you agree with me that it's quite amazing that we have here 58,000 covariates, and we see that after we do the adjustment using the propensity score, all of them have a standardized difference of mean smaller than 0.1, which is generally the rule of thumb that we use to say whether or not they're different. So on all of these characteristics, we've now made these two populations comparable, and hopefully that will allow us to get an unbiased estimate of the effect size. However, we don't know that for sure. What we would really like is an overall empirical evaluation of the study to see whether it actually produces unbiased estimates. And one way to do that is by using controls. And a control is an exposure outcome for which the effect size is known. And we could include such a control in our analysis and see whether, when we perform the analysis, we actually get the result that we know to be true. And in that way, evaluate our study. We will start off with talking about negative controls. These are controls where the relative risk is believed to be 1, so meaning there is no effect. And because this is basically a comparative effectiveness study, this gets a little bit complicated. What we usually do in these type of studies is we pick outcomes that are not believed to be caused by either one of these treatments, so not caused by Duloxetine or by Sertraline. And because it's not caused by either one of them, we believe that the hazard ratio, when you compare the two studies, should also still be equal to 1. One example that we used in our analysis is ingrowing nail, where we firmly believe that neither Duloxetine nor Sertraline causes ingrowing nail. Well, let's just start by looking at the crude estimates. So if we don't adjust using propensity score, we find that for ingrowing nail, the hazard ratio is 1.16 with a p-value of 0.03, meaning it's statistically significant. That doesn't mean that Duloxetine causes ingrowing nail, in fact, but it does mean that we think that the crude analysis is in fact biased. One way to visualize this information, and this is a graph that I will use throughout my presentation, so I would like to go over it with you. In this visualization, on the x-axis I'm showing the hazard ratio, and on the y-axis I'm showing the standard error, basically the width of the confidence interval. The nice way of display, and the blue dot is the crude estimate for ingrowing nail when comparing Duloxetine to Sertraline. And one nice thing about presenting the data in a graph like this is that everything above the dashed line has a p-value greater than 0.05, so it's what we would call statistically not significant. And everything below the dashed line is what we would call statistically significant. And we see that the crude estimate for ingrowing nail is inside of this red area. Of course, we're not really interested in the crude analysis. What if we do the adjustment using propensity score? Well, then we see that the hazard ratio moves over to 0.94 with a p-value of 0.44, meaning it's no longer statistically significant, and that's actually what we'd like to see, because this is a negative control where we believe that the true relative risk is 1. So based on this one example, we have a feeling that our adjustment for confounding is working, that we're reducing bias by including the propensity score in our analysis. But it's very hard to draw any conclusions based on just one example. It's much better to have more, right? So that's what we did. We defined a total set of 52 negative controls, where here's our ingrowing nail. So these are all outcomes that we believe are not caused by either Duloxetine or Sertraline. It's a large number of negative control outcomes, and it was a lot of work constructing these. But luckily we had some help from Larry's. If you're interested in Larry's and how it can help you pick negative controls, please see the demos later on. Basically, Larry's was able to suggest negative controls, and then we had a manual review process where we ended up with this list of 52. So here in this plot, I'm showing you all of the crude estimates for all of these negative controls. So each one of these dots is an estimate for one of these outcomes. So there are 52 dots in all. And already from this plot, you can see this is probably not very good, because most of these dots are shifted all the way to the right, and even though we expect for each and every one the true relative risk to be equal to 1, we see effect sizes ranging from, one's even over at 0.25 all the way up to 5. So that should worry us. And moreover, most of these are actually below the dashed line, meaning that they're statistically significant. We would expect 5% of negative controls to have a p-value below 0.05, because that's how we define a p-value. And instead, 68% of them have a p-value below 0.05. So we can certainly say that we found crude estimates, in this case, to be uninformative, and you should not use them for decision making. Of course, we were never intending to do that. What we're really interested in is the adjusted estimates, and we see that after adjustment, this picture looks a lot better. Most of these estimates have moved closer to the true relative risk of 1, and now only 16% have a p-value below 0.5. So that's already much closer to what we would really like, but not quite there. In the past, in OMOP symposiums, we've talked to you about p-value calibration. And what we did there is we've shown you how you can perform p-value calibration by first realizing that the p-value represents the probability of an estimate when the true relative risk is 1. Now that we have these negative controls, we can use those to provide an empirical distribution of estimates when the true relative risk is 1. So basically, they represent the null hypothesis and the estimates that you could observe. And with this empirical null distribution, we then can compute a calibrated p-value. And so in this plot, I'm showing you a visualization of that p-value calibration in the sense that this orange area that I just added is the area where the calibrated p-value is smaller than 0.05. What you see is actually that this orange area isn't all that different from the area denoted by the dashed line. In fact, only when you get very close to 1 does it diverge from the dashed line. So in a sense, these estimates weren't really that biased to begin with. We didn't need a lot of adjustment to make them calibrated. After p-value calibration, we find that 4% of these estimates have a p-value below 0.5, and it was 16% before. That's all good, but this is only telling us how the method performs when the true relative risk, or the true hazard ratio in this case, is equal to 1. But it doesn't tell us anything about when the hazard ratio is not equal to 1. And so one worry that we might have is that our method is biased towards the null. And so it's very good when the null is true, but it's not so good when the null is not true. So what could we do about that? Well, we could include positive controls in our study, but there is a problem with positive controls. So positive controls are things where we know the relative risk, but we also know that the relative risk is not equal to 1. Well, one problem is that often you find very few positive examples for a particular comparison. So in this case, you will be hard-pressed to find examples where it is known with certainty that an outcome is caused more by Duloxetine than by Sertraline. Even if we do find them, the exact effect size is usually never known with certainty. And I would argue that effect size typically depends on your population anyway, so it's hard to know with certainty at all. A third problem with positive controls that was pointed out by Nicholas Noren in this paper is that if we're all in agreement that they're positive controls, that probably means that the doctors know they're positive as well, and they will change their behavior accordingly, like taking action to mitigate the risk that the drug poses. So all in all, we realized that, well, positive controls are really hard. But what if we could just create some ourselves? So how do we do that? What if we start with a negative control, where we know that the relative risk equals 1, and we simply add simulated outcomes during exposure of one of the drugs until we've reached the desired relative risk? I'm going to make it a little bit more complicated because we would actually like these injected outcomes to behave like real outcomes. We would like to preserve the confounding structure, and the way that we do that is by we try to inject these outcomes for people that are already high at risk. So for example, if we find that a particular negative control outcome is more likely to happen in people with diabetes, well then these new outcomes that we're injecting, that we're simulating, will mostly occur in people with diabetes. So just to give you a graphical representation of what I'm talking about, so here I'm showing 6 example patients, some of them on Duloxetine, some of them on Sertraline, some experiencing the negative control outcome in growing nail. And in this very simple example, I've made the relative risk equal to 1 because there's one person on Duloxetine that has the outcome, and one person on sertraline that has the outcome. I fitted a model that predicts who gets ingrowing nail, and I'm using that model to identify that, well, maybe patient 5 is at high risk for ingrowing nail, but actually doesn't yet have one. And so that is the one where we will add a new simulated ingrowing nail. What we've now done is we've changed the true relative risk from 1 to 2, but with the same confounding structure as we had before. So we can do this for each and every one of our negative controls, and we can inject relative risks of in this case, 1.5, 2, and 4, and we can then estimate for all of these negative and positive controls using our study design. So in this graph, what I'm showing you here is the black line indicates the true hazard ratio, and all these dots and lines represent the point estimates and confidence intervals that we have for each and every one of these positive and negative controls. So for example, here's an estimate for the original ingrowing nail, which was a negative control, so the true relative risk was 1, where we estimated the relative risk to be 0.94. Here is the estimate for ingrowing nail plus, where we changed the relative risk from 1 to 1.5, and our method, our study design, estimates a relative risk of 1.47. Ingrowing nail plus plus, ingrowing nail plus plus plus. And so we did this for all of our negative controls. So we now, all of a sudden, have this information on how the method performs when the relative risk is not equal to 1. One thing that we can see from this plot is that these relative risks tend to move pretty nicely with the true relative risk. So in case we might be worried that this method is biased towards the null, this plot is telling us that we shouldn't worry about that. These estimates are moving with the true relative risks. We can also look at the coverage that we're achieving. And so the coverage is the percent of times when the true hazard ratio is included in the 95% confidence interval. And so we would like the coverage to be 95%, but we see that for the various true effect sizes, that is actually not the case. So for example, we see that a coverage of 83% means that the true effect size is outside of the 95% confidence interval 17% of the time when the true relative risk is 1. We also notice that coverage decreases with true effect size. For example, if the true relative risk is 2, we're actually missing 30% of the time the true hazard ratio in our 95% confidence interval. So that's not good. How can we fix this problem? Well, just like we did p-value calibration, now that we have this information, we're actually in a position where we can do confidence interval calibration. For those of you who may realize this, when we do p-value calibration, what we do is when the true relative risk is 1, we estimate the systematic error distribution using the observed estimates for these negative controls. And we assume that this distribution, this error distribution, is a Gaussian with a mean mu and a standard deviation sigma. Now that we've created our artificial positive controls, we can do that same exercise when, for instance, the hazard ratio is 2. Again, compute our mu and our sigma. Instead of computing it at every different level of the true relative risk, we can also just posit this model where we believe that mu and sigma are just linear functions dependent on the true hazard ratio. So in this case, we have, for mu, we have an intercept and a slope relative to the log of the true hazard ratio, and we have a similar function for the sigma. The way that the confidence interval calibration process works is we start with all the observed estimates that we have for our positive and negative controls, and we use those to estimate those 4 parameters of our model, the 2 intercepts and the 2 slopes. Once we have those, we're in a position where we can now build a simple mathematical transformation where in goes an uncalibrated point estimate and confidence interval, and out comes a calibrated point estimate and confidence interval. In this situation, what we noticed that these confidence intervals were too narrow, And so what our calibration procedure ended up doing was simply making the confidence intervals a little bit wider to get us back to nominal coverage, meaning that a 95% coverage confidence interval has 95% coverage. Doesn't always have to be this way, it's just the way that it turned out in this situation. But luckily the calibration uses the observed estimates to detect what is going on and adjust for any problems it finds. So just as an illustration, what I'm showing here on the left-hand side are all the estimates and confidence intervals that we had before calibration, and on the right-hand side, for those same positive and negative controls, what if we apply this calibration? And you're seeing that really not that much changes, except that the confidence intervals get a little bit wider. But as a consequence, if we look at coverage, we see that these confidence intervals now have nominal, near nominal characteristics, meaning that actually almost 95% of the time, the true hazard ratio is within the 95% confidence interval. And so confidence interval calibration can complement p-value calibration, and I hope you share my excitement about this development in the sense that quite often we're not so much worried about a p-value and whether or not we can reject the null. We're more interested in getting an understanding of the real magnitude of an effect size and the uncertainty around that magnitude. And that is something that we now can do with confidence interval calibration. So let's think about the evidence that we currently have for stroke. So we have the results from the where they basically show this table where with a accrued and adjusted hazard ratio with the point estimates and confidence intervals and p-values. And really not much more than that. So it's very hard to interpret these results and get an understanding of how we should think about these results. In contrast, what we're proposing is that we provide this information. So here I'm showing real results for Duloxetine versus Sertraline for the outcome of stroke for 4 databases, so CCAE, Medicaid, Medicare, and Optum. On the left-hand side, the uncalibrated point estimates and confidence intervals, and on the right-hand side, the calibrated point estimates and confidence intervals. In addition to this information, we're also providing the context I think that you would need to interpret these results. So we're providing the diagnostics that we think you need, and we're providing the results of this this evaluation where we use both negative and positive controls to determine whether or not our analysis was biased. And of course, the nice thing is that all of this information about the performance of this method is now incorporated into our calibrated estimates. And so, even though in this particular example, our results are actually pretty comparable to Lee, Lee's point estimate and confidence interval, I think, are subsumed by our point estimates and confidence intervals, I think we provide more context to interpret these results. And so I think that's a very valuable contribution. So, in short, our recommendation for evidence evaluation is, well, you should always produce standard diagnostics. So for a cohort study, you should always diagnose the propensity score distribution and covariate balance. You should always include negative controls to estimate the error when the null is true. And you should always create positive controls to estimate the error when the relative risk is not 1. Once you've done that, you're in a position to calibrate your p-value and your confidence interval, restoring the nominal characteristics of these two statistics. All right, going to the last bit of my talk, talking about evidence dissemination. How do we share evidence to inform decision making? Well, so traditionally, evidence, as I've just presented to you, is disseminated through scientific literature. Just like Lee did, we could write a paper, include all the evidence that we have, and hope that it gets published somewhere. Well, how well does that process of dissemination really work? And to answer that question, what I did is a very simple exercise. I wrote a small program that basically runs through the literature, all of observational research papers that I could find, and extracts from them just the effect size estimates and the confidence interval. So in this case, from this particular abstract, it got the odds ratio two odds ratios and their confidence intervals. Once I did that for a number of papers, I could then draw this plot. Every dot in this plot represents one of these estimates from one of these observational research papers. In total, there are almost 30,000 dots from almost 12,000 papers. And so, of course, all of these estimates are for very different things, for very different exposures and very different outcomes. But I still think we can learn something from by looking at this plot and looking at the pattern that's quite obvious, actually. What you'll probably notice is that this area above the dashed line, where things are not statistically significant, is rather empty. Most of these estimates are below the dashed line, most are statistically significant, and we also notice that there's quite a sharp boundary at the dashed line, meaning that there's probably some sort of an artificial process that is making us not see things that are not statistically significant. There are more things to notice, like these estimates tends to cling to the underside of the dashed line, but that's all. We could talk quite a while about this plot, but I think most importantly, we see that 85% of exposure outcome pairs that we've produced as observational researchers and have published has a p-value below 0.05. And that certainly is not what I would have expected. I think most exposures, most drugs do not cause most outcomes. Most drugs do not cause heart attacks, only some do. Most drugs do not cause stomach bleeding, only some do. So I certainly wouldn't expect 85% of things out there to show a real effect. I would imagine that number to be much lower. So what is going wrong here? Well, three things, I think: observational study bias, publication bias, and p-hacking. And in order to explain these three concepts, I made up these simple cartoons. So first off, observational study bias. The patient walks into the doctor's office and says, "Oh, I have a headache and my stomach really hurts." The doctor says, "I'll prescribe drug A for your headache. It's safe for people at risk of stomach bleeding." And 1 week later, the patient comes back and says, "I took drug A, but now I have a stomach bleeding." And along comes the observational research scientist and says, "Ha, drug A causes stomach bleeding." Which is, of course, not the right conclusion, probably not the right conclusion to draw in this situation. And although this particular cartoon might seem a bit unrealistic, of course, this is exactly what is happening where we have unmeasured or unmodeled confounders that we don't include in our data, and we falsely conclude that some association is due to a causal relationship. Publication bias is in this cartoon. Try to explain this in this cartoon, where somebody comes in and says, "Jelly beans cause acne," and the scientists are ordered to investigate, and they find no link between jelly beans and acne with a p-value greater than 0.05. But then the same person says, "Well, I hear it's only a certain color that causes it," and the scientists are ordered to investigate. They look at 20 different colors of jelly beans, and for one of them, they find a p-value below 0.05. And that's the thing that is reported in the literature, that in this case, green jelly beans are linked to acne. And of course, the joke of this story is that if you do 20 studies, you would expect around one of them to have a p-value below 0.05, even if the null is true for all of them. Again, this is maybe a little bit unrealistic. What in reality happens quite often is that researchers try out different topics and then they stick to the one that produces a statistically significant result. But if they do that and we see their result, we don't know whether that's actually really statistically significant or it was just the 20th study that they performed and we're just looking at a spurious result. The third phrase that I threw out there is p-hacking, where a professor walks in and says, "PhD student, I think A may cause B, go investigate." And the student says, "Yes, professor. I ran the analysis, P is greater than 0.05. And then the professor says, "But did you adjust for confounder Z?" And the student says, "Well, no, let me get right back to you." And then after adjustment for Z, P value is smaller than 0.05, and the professor says, "Yay, let's publish a paper." So this is a little bit more subtle than publication bias, but it's actually the same problem. Because in publication bias, we try different questions until we get an answer that's statistically significant. In p-hacking, we stick to the same question, but we try slightly different ways of answering that question until we get a way that actually produces a p-value below 0.05. And this actually, I must admit that p-hacking probably is the biggest problem out there, in the sense that I see many people practice this art of p-hacking without even realizing that they're doing something wrong. So if these are the problems, is there a solution? Well, I would like to propose one solution. What if we stop doing one study at a time? For example, what if we consider all outcomes? So here are the 22 outcomes that Patrick already listed, where somebody thought really long and hard about the exact definition for these outcomes, how we should find them in our data. Why not look at all of these 22 outcomes when we're comparing Duloxetine to Sertraline? So here are the results for all 22 outcomes as generated from our data. So what I'm showing you here is results for all 4 databases for the 22 outcomes. And just to be very clear, what I'm showing here are confidence intervals and point estimates that are all calibrated. So in every database, we perform the same process that I just explained, where we use negative controls and we generated positive controls using a fancy outcome model and whatnot. And we use it to produce these calibrated confidence intervals. So we're actually quite certain that these confidence intervals are showing nominal characteristics. I also just talked to you about publication bias and saying if you do 20 studies, you would expect at least one of them to have a p-value below 0.05. So I made sure to also correct these confidence intervals for multiple testing, which you should of course always do if you're looking at these many results. So keeping that in the back of our head and looking at these results, and just to orient you, blue means the confidence interval includes 1 and orange means it doesn't. We see that there's really not that much going on. Maybe for diarrhea and alopecia, there's a difference when using Duloxetine versus Sertraline. But overall, not a very exciting picture, and certainly not something we probably would get published because most of it is not statistically significant. However, for a patient, this might be very valuable information. If a patient is deciding between Duloxetine and Sertraline, we can now tell them we've generated quite a lot of evidence, and that evidence suggests that for these 22 outcomes, there's not much difference between these 2 drugs. All right, but what if we take this one step further? What do we consider all treatments? So here are the 17 treatments that Patrick already mentioned before, 15 drugs for treating depression, and 2 procedures. What if we generated evidence for all of them? So we have 17 treatments. That means we can make 272 comparisons. We have 22 outcomes, so we can almost generate 6,000 estimates, and we have 4 databases, so almost 24,000 estimates. What if we did that? Well, of course, that's what we did. It's important to note that for all of these, we generated propensity score models specifically for those comparisons. And I'm showing you just very briefly here all of these propensity score distributions just for the Truven CCAE database. I'm of course not going to go discuss all of them, but it is interesting to see, maybe you can see it or maybe not, that some of these comparisons, actually there's a very large overlap in propensity score distribution, so they're good comparisons. And for others, they're completely separated, so they're probably very bad comparisons. So what I'm showing you here is the results of our exercise. So all of these dots are the estimates that we produced. And one thing I would really like to stress here is that each of these estimates has been generated with that same process that I just showed you for Duloxetine, Sertraline, and stroke. So each of these estimates has full diagnostic and evaluation available. Just to pick a random example, fluoxetine versus psychotherapy for the outcome of suicide ideation in the Medicare database, we find a calibrated hazard ratio of 1.05. And we not only have that, we also have things like the propensity score distribution plot and other diagnostics criteria. Just to make a quick detour here, if you look at these graphs there, it's actually quite interesting what's going on for this particular example. We see that the propensity score distributions are not really that overlapping, so there's lots of difference between users of fluoxetine versus people initiating psychotherapy. It's maybe not surprising. We see that the covariate balance that we achieve after adjusting using the propensity score actually tells us that we're able to correct for these differences. But we also see that if we look at the bias distribution plot, and I know you can't really see it, but so take my word for it, we see that there's actually, even after propensity score adjustment, a lot of residual bias. And we also see the same thing in our estimates for positive controls. But luckily now all of that information, the fact that we're actually still very biased in this analysis, is incorporated into our calibrated confidence interval and point estimate. Another random example is mirtazapine versus citalopram for the outcome of constipation in the Medicaid database, where we find a hazard ratio of 0.9, and well, the story is actually less exciting than for the previous example. Here we find that we actually produce reasonably unbiased estimates even before calibration. Now, these estimates are much closer in line with what were my expectations. Only 11% of the exposure outcome pairs have a calibrated p-value below 0.05, meaning that probably most of these things represent situations where the null is true, where there is no differential effect between the two treatments. And only a handful of them, there really is a difference between two treatments. Contrast that with what we found in literature, where 85% has a p-value below 0.05. I think this picture that we just generated is much closer to the truth of the reality out there. Again, to stress, each estimate that we produced here was produced with the same rigor as I discussed earlier that we recommend for all studies. And I would claim that we could probably publish each and every one of these estimates as a paper that would pass peer review. Although, of course, the ones that are not statistically significant are not as likely to get accepted. But each of them, we used propensity score adjustment, we used the Cox regression, we calibrated using negative and positive controls, and we did all of the other things that I mentioned before. Again, this is not data mining. Not to say that data mining is a bad thing, but it's not what we're doing here. All of these results should be interpreted considering multiple testing. So like I showed you before, if we're picking out 22 estimates from this cloud, we should adjust for the fact that we're looking at 22 estimates. I would argue this is something we can't do for literature. If in literature we find a paper and we would like to adjust for multiple testing, we can't, because we're only seeing the things, mostly seeing the things that are statistically significant, and we don't know how many studies have been done out there that we don't know about, but that we should really be adjusting for. So, in short, our recommendations for evidence dissemination, well, I think what you need to address, and what we addressed, is observation study bias. And the way that we did that was by adjusting for confounding and by verifying that the bias was addressed. And you should always disseminate your diagnostics and evaluations. I think we addressed publication bias, and we avoided publication bias by showing all the tests that were performed, not just the ones that were statistically significant. And I would even argue that we addressed p-hacking, because it now becomes very hard when you do analysis like this to fine-tune your analysis to get the one specific result that you were after. So, wrapping up, our recommendation for evidence generation is you should write and share your protocol, you should use open source study code, use validated software, and replicate across databases. For evidence evaluation, we argue that you should always produce standard diagnostic, you should include negative controls and create positive controls, and always calibrate your confidence interval and p-value. And for evidence dissemination, you shouldn't just provide the effect estimate, you should always include the protocol, the study code, and any diagnostics and evaluations that you may have generated. And you should produce evidence at scale, not stick to one study at a time. What I would like to see, and what I think where we're going, is that a situation similar to the Large Hadron Collider, where instead of researchers each on their own generating one piece of evidence, one estimate at a time, we as researchers come together to work at a single process by which we generate evidence. So in this case, researchers coming together to build a large hadron collider to generate the evidence that we need. And with that, I hope you come and join the journey and join us for this. Thank you.